Thank you. First of all, very grateful to KIT for providing the fellowship so that I could come and visit, and to Professor Ehret for, that's the last time I'll call you Professor Ehret, to Uwe for hosting me, and it's been wonderful. I think I've tried to organize the talk into three parts. One is to sort of bring you up to speed with the motivational side of things, then a little bit of background about machine learning, and then I'll show you some examples from research I've been doing with a student of mine. Okay, so what we're interested in is building models of Earth systems. And so this is just an illustration of an Earth system. It's dynamical, you have rain falling, it generates various state variables in the system, and you get runoff forming and so on. And we can model this kind of system at many different levels. One of the simplest is you build what we call these physical conceptual models that are relatively simple, but they're easy to build. And they're very commonly used by people who are doing operational things like designing dams, doing flood forecasting, that kind of stuff, because they're easy to understand, they work pretty well, and they're not too complicated. They just focus on dominant mechanisms. On the other side, scientists like to work with these very fine, detailed, causally resolved models where you put in a huge amount of detail. If you can think of it, you try to put it in, right? So that's on the other side. And then we now have this new field that's emerging. Well, it's not new. It's been there since time immemorial, but has really taken off recently. And it's the idea of just using data. If you have a lot of data, instead of worrying about physics, you just throw the data into the model and you build a model, right? So data-based models. But let's look at the stages of building a model. So let's say we've got a physical system, and we've got some prior understanding of how the world might work. And we go ahead and collect some data. I think you'll agree with me. The first thing is you just have this internal physical conceptual model in your head. That's a model too. Sorry, a perceptual conceptual model in your head. And it's going to be affected by the things you've been taught. It's going to be affected by what you see that's going on in the world. And all of us navigate the world with these models, right? And then you might spend some time and you might formulate this into a conceptual model. You might write things down, draw pictures on a board, write papers about it. And at this level, you can communicate with other people about it. The one that's in your head, you can't share with anybody, you have to write it down. Let's call that a conceptual model. And you have to make some assumptions about physics. You have to make some assumptions about what's important and what's not important to the architecture. Then you might convert that into, in the old days, you'd convert it into a physical scale model, to, like you build a wind tunnel model or something. Nowadays, we mostly convert it into a mathematical model where you have to make some more assumptions. And then you find a smart graduate student and you ask him to code it up and run it through a computer. So now it's going from equations to algorithms. And then you run those algorithms on your computer and generate some simulations. You test it and you go around the circle over. If it's not good enough, you sort of go around. And the point here is that when you talk about models, it's a little bit of an ambiguous term, right? You could be talking about the perceptual conceptual model in your head. You could be talking about that conceptual model, which we all are able to communicate with each other, whether you're an expert coder, computer scientist or not. The mathematical model is usually just the domain of the nerds, right? People who are worried about the formal logic. And then the computational model is even more the domain of the computer science nerds. They really understand what's in there. Most of us don't. Okay. What about when we do machine learning? Okay, you start from the same place, but instead of that process of trying to figure out what's going on, the physics and so on, you basically say, well, based on the problem I'm trying to solve, I just look for a suitable machine learning architecture, and I just use that. I take advantage of the universal approximation theorem. I just take that, feed my data through it, train it. I still do the coding step, build a model, and I go around this. Okay. So there's some similarities and some differences. Okay. So let's take a look at the similarities and differences. On the left, I've got this physical conceptual modeling approach, what scientists have been doing since before we had computers. And then on the right there, I'll say the properties of the modern machine learning sort of based approach. So let's talk about the focus, objective, and strategy. In physically based modeling, at least of earth science systems, we're interested in mass, energy, and information flows. We're interested in causal relationships. We want our models to be fairly simple and interpretable. But the net result of that is that they're usually what I call overcompressed. They don't really represent everything that's in the data. You've lost some information. And the way we know that is because when you try to compare them against observations in the real world, they fail to some extent, right? They do okay, but maybe not as well as some other as machine learning models might do. On the other hand, your machine learning model just focuses on information flows, doesn't worry about conservation constraints maybe, and they just look for patterns in the data. And then based on those patterns, correlational strength, they are able to figure out what causes what in some correlational sense. So there's no causality necessarily in those models. They focus on performance, and right now they're very popular. And so people are saying, why would you want to use a science-based physical model? Because I can give you better flood predictions using this machine learning approach. What are some prior assumptions? In physical conceptual model, you assume a control volume. It may or may not be valid, right? There's some questions about whether those control volume assumptions are valid. They're constrained to obey conservation, which is a very strong regularizing principle, whereas the machine learning models do not need to make this control volume assumption. It may be implicit in the data that you feed them, and they're not constrained to obey conservation, although there's some hope that you might, in principle, be able to learn conservation principles if the data are sufficiently good to help you do that. And then if you look at the architecture, a little bit, as I mentioned earlier, in the physical approach, you specify the states, you specify the connectivity between the nodes, you specify the equations, and they have meaning to you as a physical scientist, typically, maybe, not always. And then you just train the parameters. That's all you do. You take your model, it's off the shelf, maybe you modify it a little bit, and then you just train the parameters and hope it works. On the other hand, one of the advantages of machine learning models is that you can learn the number of state variables you need, you can learn the connectivity, you can learn the flux equations, and there's some question in the literature now about, so are these models interpretable? So I put a question mark because I'm not sure that they are not interpretable. I think they actually are. And you train the parameters, and again, there's some questions to whether they're interpretable or not. And I still think that maybe they are, but this is a point of discussion. The basic point is that in physical modeling, the form of the structure of the model is very strongly specified beforehand, before you start your application. And that's based on physical understanding. Whereas in machine learning model, the architecture is only weakly specified. And you take advantage of this thing called the function approximation theorem, which basically says if you formulate your problem as an artificial neural network, you can pretty much learn any relationship, input-output mapping, using that mathematics. Okay. So in the case of physical modeling, when you train your model, the learning only can penetrate to parameters, whereas in the machine learning model, it can penetrate all the way down to architecture. So in the physical model, if you think your model is not good enough, you have to yourself figure out how to modify it and improve it. And the idea is that the machine learning model can take away some of that task from you, and the computer can actually automatically do that for you. Okay. All right. Let me show you some basic examples of this from some studies that a couple of students of mine have done. So this is Yuan, who's got this paper published in WRR, and he got interested in this problem of modeling snowmelt accumulation, snowpack accumulation and melt over the continental US, very large area. You've got about 1/3 pixels, so it's very computational. He's got about 20 seasons of data. And we had to use a kind of a statistical approach because we couldn't model it every single pixel. So we sampled pixels in some stratified way. Prior to this, some work had been published in the hydrology literature suggesting that the LSTM, long short-term memory networks, were sort of the best thing that you could build in order to do this kind of prediction, but they were applied in streamflow forecasting. So Yuan decided to apply it to this area, which nobody had studied at that point, and I don't think anybody else has yet either. So he may be the only one so far. So we're going to model over the entire continental US, but just these 5 selected regions. And we're going to compare it to the SNO-17 snow model, which is used by the National Weather Service right now for snowmelt prediction, particularly in the context of flood forecasting. So this is a physical conceptual model. So this model uses rainfall, air temperature, and elevation as inputs, and it computes snow dynamics as outputs. This is a much simpler model. We can build this model as a single model for the entire continental US, not worrying about location. We can build a version region by region, or we can build a model version pixel by pixel at every single location, okay? So we're gonna have 3 versions. And we're gonna look at performance. So what this is a cumulative distribution function on the y-axis of metric performance, where 1 is perfect, okay? It's an efficiency metric. And the CDF is from 0 to 1, which means all the pixels. And the performance metric is on the x-axis, and that goes from -infinity to 1. I'm just showing you from 0.5 to 1. And so going to the right is better, okay? And so what this shows is that when you take the SNO-17 model and you model the entire continental US as a single set of parameters, right? You're not taking into account location. You get about 50% of the pixels have an efficiency above 0.75, but 50% of the pixels have a much worse performance. Okay, that's what that horizontal line means, the median. If you then take that model and you break it up region by region, of course, you would expect performance to improve. So that's the blue line there. And if you now train it pixel by pixel to every single location, this is the line you get, okay? So this sort of reflects the range of performance you can expect from this model, with the red line being the worst possible and the black dotted line being the best possible because you're training it to each location, okay? All right, now we take the LSTM network and we train it on the same data, absolutely the same data. We use the same hyperparameters and architecture as Freddie Kratzert used in his streamflow modeling paper. And so there's the LSTM. And training one model for the entire continental US, right? One set of parameters for the entire continental US, that's the performance you get, okay? So you can see median performance is above 0.95 already. And then if we take the same model and we break it up region by region, presumably the snow dynamics are different in different regions, you actually get almost no performance improvement, which is kind of remarkable because even though we're feeding in static characteristics and so on, none of this helped. It basically taught us that the most important thing about snow dynamics is contained in the hydrometeorological data itself, not in the local terrain and elevation and all of that kind of stuff. There may be some benefit, but it's not huge, okay? And if you look at this, basically, we're saying that about 90% of the locations we're getting better than 90% efficiency, which is actually quite remarkable. Okay, there are some locations where the efficiency is not so good, but they're very few, and so we should probably focus on why in those regions. But at least for this study, we didn't get into that too much. So we actually learned something interesting, right? If you're a physical modeler, you'd like to know what do you need to pay attention to. And so this is an example of using machine learning model to help you improve your physical sense. Okay. Just to show you that the performance is uniformly good across the country, all the red pixels basically have efficiency metric above 0.9. Okay, so it's not something which is spotty. Okay. And we did one additional thing, which is so the original LSTM was trained with precipitation, temperature, and elevation, where elevation is used in order to compute atmospheric pressure in the model. And then we took out elevation. Okay, we said, what happens if I don't give you elevation? And performance goes down. Okay, so there's something interesting and valuable about the local characteristic of elevation. But what if I leave elevation out and I give it all these other meteorological variables that are available to me? Dew point temperature, vapor pressure deficit, long wave radiation, short wave radiation. And performance actually improves. So what does this tell us? It tells us that the hydrometeorological variables already encode within them information which is being provided by elevation, okay? And that sort of makes sense if you think about it in retrospect, because the landscape co-evolves with climate, and the vegetation co-evolves with climate, and so on. So you would expect there to be some correlation there. So this might help us understand why, without feeding in static variables, without doing regionalization, we could build a single model for snowmelt dynamics across the entire US. Now, this needs to be verified, but I'm just saying it's very strongly suggestive, okay? So we knew that Snow 17 had room for improvement, but we didn't know how and why and where. Well, I'm sure there are people who study snow dynamics who could have told you this before. I'm saying I didn't know how and why and where, and I learned this from this. I learned that snow dynamics is to first order largely insensitive to local static properties, and that it's beneficial to include additional meteorological variables, but you need to figure out how and why. Okay. So the most important thing is, well, on the one hand, if you build a machine learning model, it also tells you what's close to the best possible performance you might be able to get with a physical model, okay? Because it does a better job of exploiting all the information that's in the data. It gives us some insight into what to pay attention to, and it does provide some guidance to help you improve your physics-based modeling. I'm just going to remind Uwe about the unicorn, and I'll tell you later what the unicorn's for. Okay, a second study by another student of mine who did his master's work with me and is now going on to do his PhD. This paper is in review. He basically applied machine learning now to the problem of modeling snow stream flow, catchment scale stream flow across Chile. And you can see that Chile north to south is actually as long as the United States is wide east to west. So but it goes north to south. So it's got this huge range of hydroclimatic characteristics. Okay, so it's a challenging problem. What do? We said, if you just use one approach to model the system, you learn something, but you're much more likely to learn about the system if you use many different representational approaches. You feed the same data through many different perspectives, kind of like the blind men and the elephant, or the blind people and the elephant. You get a different view on the same problem, right? It's not having multiple hypotheses, it's having multiple perspectives, which we think is much more powerful, okay? So on the left here, I've got a physically based model. In the middle, I've got the long short-term memory network, which is also a dynamical model, but this one conserves mass. This one just does flows of information. And then here you've got this decision tree approach, which is pretty well known. It's a random forest approach. And what it does is it sort of partitions the data set and says what's important for my prediction and what's not important for my prediction. So this is kind of like your go-to machine learning algorithm, the random forest. Before you do anything else, do a random forest, right? And then you hope to be able to beat it in performance. All right, so about 320 or so catchments across Chile from north to south. And here's again the cumulative distribution function on the y-axis, metric on the x-axis. Note, of course, that 0, you want to be better than 0. Okay, so there's some places where performance is really bad. Okay, and better is to the right. Okay, so again, you've got your median metric over there, and the blue line is your long short-term memory network. We sort of expected that. Okay, it's going to do the best because it has inbuilt dynamics and it's very efficient at using information. The green line is your random forest. And interestingly enough, your physically based model there is not bad at all, right? This is a GR4J French physical conceptual model. And it does at least as well as the random forest in the regions to the right, which are mostly humid, wet regions. You'll see this later, and the ones where it does poor are mostly dry, arid regions, okay? Okay, so, all right, fine, but that doesn't really tell us a whole lot. So what else could we learn? Well, the first thing is you notice down here that there are places where the physical model is actually better than the LSTM. Okay, it's not very good because the performance is pretty bad, but it's still better than the LSTM. And so that suggests that maybe there is some value to regularizing information in the physically based model, the conservation principles and so on, okay? But here's an interesting thing you can do with an LSTM, which is hard to do with a physical model. So these are different cumulative distribution functions, again, metric going to the right, and we varied the sequence length of data that we feed into the model, okay? If you're not familiar with an LSTM, it's got a Markov memory chain, but you also can feed it past information, 2 days, a year, you know, as long as you want back, and it has the ability to exploit that information, okay? So if you only feed it a sequence length of 2 days, you get this curve. If you go up to 8 days, you get a significant benefit. Okay, that makes sense. Maybe 8 days of past precipitation is valuable and useful, climate information. When you get to 32 days, up at the top on the right, you notice that the improvement stops after 32 days, okay? But there are certain catchments, or many catchments, where you have to go all the way up to 270 or 300, up to a full year of information in order to get benefit, right? So down here on the bottom, 32 days is clearly not enough. You get very significant improvements by feeding in information from the distant past, okay? So, and as I pointed out earlier, the ones on the right up there are usually the wet regions, they're easier to model. And so you only need about 30 days memory, whereas down here in the drier regions, you may need up to 365 days of memory. And this kind of thing is harder to discover with physical conceptual models. I think this is intuitively, you might expect that that's true, because if I ask you to make a prediction of stream flow for tomorrow, based on what you know, if you're in a wet region, you can do a pretty good job. But if I take you to Tucson, Arizona, and ask you what tomorrow's stream flow is, it'd be a little bit harder to predict it accurately. Yeah, okay. But here's the really interesting thing. So what we did was we took the performance catchment by catchment, but now we sorted them from left to right in terms of aridity of the local area. Okay, calculate the aridity index, and that's on a log scale. There's a vertical line there, which means all the catchments to the left of that are energy limited catchments. That means you've got more water and you're limited by the amount of energy you have available in order to evaporate it. Whereas to the other side, you're water limited, right? You've got lots of energy, dry regions, and there's not enough water. You can't use up all that energy, okay? And what do you notice? There's all three models. All three models decline almost log linearly with aridity, okay? So apparently it doesn't matter what modeling technique you use, performance is going to get worse, okay? And this immediately reveals to us that, that there's something missing in the data itself, okay? So there's a data limitation. The reason why you're not doing well on some of those catchments doesn't have anything to do with the modeling scheme you're using. It has to do with whether you're providing the information you need in order to do a good job. And the fact that all three of them decline is what gives you confidence that it's actually a data problem, not a model problem, okay? So, so there's benefits to using a multi-representational approach. So you're using a physical approach and different kinds of machine learning approaches. Okay, so same thing. You can supplement physical modeling to help understand the system, and you can learn something about your data that it's good enough for you. Okay. All right. I'm running. I've only got to part 2 and I'm running behind here. So what's my interest? My interest is in bridging the gap between this physical, conceptual, and machine learning approach. And how do we do that? Well, I set myself the task of digging into machine learning and trying to understand what was under the hood, and then trying to see if I could relate that to what I understood about physical modeling, okay? So let's take a very simple machine learning architecture, artificial neural network, and look at that. So typically what happens is you get a picture which looks like this, but I'm breaking it down. So on the left is all your data that you're feeding in as inputs. What you do is you multiply your data values by some weights. Basically, you just do a linear equation, and then you pass it through a nonlinear activation function, and you get what's called a feature, right? You learn some characteristic property of the data. And then you do that many times in parallel, and you get a bunch of different features. Then you take those features, you multiply them by weights, you basically just do a linear interpolation amongst features, and you map that to your output. And in the beginning, you don't know what these weights should be, so that you train it with some data, right? You use backpropagation, you train your model, it figures out what these weights could be, and then it gets to be a very good predictor, okay? And things like this are being used all the time on the internet to tell you what movie to watch next. And, you know, when you do a Google search, they use this kind of technology to tell you, to find pages for you and so on. Okay. So your activation functions typically look something like this. They're either thresholds or these logistic curve sigmoid type functions, okay? The important thing, the take-home message here is that, first of all, these weights are constant. And the idea is you want to learn features of the input data that you can then combine linearly, okay? So think about it, if you've got an image and you want to be able to train your machine learning algorithm to tell you that it's a cat, you want it to learn features like ears and whiskers and nose and so on and so forth. And then once it's learned those features, you want to be able to easily combine them together in order to tell you, okay, that's a cat, not a dog or a bird or something else, okay? In order to make it easy to learn, this linear property is important, okay? And so you want to learn features that can be combined linearly, because if it's nonlinear, as we all know, it becomes very, very difficult, okay? And then you can organize these in layers and build a hierarchy of structures. You can do, so that's a static relationship thing. You're just mapping from static data to a static characteristic. You can feed in your data as time delayed, lagged stuff. You can use exactly the same neural network. Now you've got time varying inputs. Now you have time varying features, but the weights are constant. And you get a time varying output. So now you can use this to do flood forecasting or other kinds of prediction problems. And the idea now is to learn these time varying features that can be combined linearly. And you might not have thought of this, but this is essentially convolutional neural network, which is used for image processing, but actually we use it just to do forecasting, okay? And then you go another step further, where you've got these time varying features, and you can feed back from one time step to the next. So you can tell the model that at the last time step you learned this, so I'm going to tell you what that was at the next time step, right? And so that's kind of like a feedback loop, and it sort of puts momentum into the system. It smooths the behavior of the system, so that even if the inputs are varying very fast, your internal state variables of the model vary slowly as a kind of time varying momentum thing, okay? So you have many of these feedback loops in there. Again, all your weights are constant. You learn a time varying output. And so the idea is that you have these time varying Markovian features. Okay. So let's take a look at this network, okay? You basically have an input. You have this sort of thing that you can think of as a tank, storage. It's got a state variable that it's updating through this time delay feature and calculates an output. It takes the input, multiplies it by a weight, adds it to this state, takes the output, multiplies by a weight, and uses it to calculate the output. And then it feeds back some part of last time steps value back in, okay? So fairly simple architecture. And if you write the equations, they look like these linear equations. The output is a linear function of the state is a linear function of the past state and the inputs, okay? And the learned weights are constant values, okay? Then there's this thing I mentioned earlier called an LSTM, which did so well. Remember, 90% of the pixels better than 90% efficiency. Why did it do so well? It did so well because these things that were previously constants, it actually replaces them with time variable quantities, which I'm going to call gates, okay? So it's still multiplying the input by this value, but this value changes with time, and it changes in a context-dependent way. And what you learn in an LSTM is the context dependence of these weights. So it makes this thing which was rigid into a much more flexible modeling system. It's called a gated recurrent neural network. The equations, you'll notice, look exactly the same, right? They're the same linear equations, but now you've got these time varying constants here, right? They're not parameters, they're gates. So these constant weights are replaced by time variable gates. The gates are then learned functions, okay? You push the learning back one step, okay? And these gates are basically learned using these activation functions that we talked about earlier, these nonlinear activation functions, which are a function of something, which you can call the context. The context is often learned as some linear combination of past data that you feed it. And this is that sequence length that I talked about, that you could feed 2 days or up to a year's worth of past data in, okay? The activation function can be something as simple as a logistic sigmoid function, which varies between 0 and 1. Or you can use an artificial neural network and learn some much more complicated function like that, okay? So there's the basic unit that we talked about. And we now know that this unit has two kinds of memory. It's called Markovian memory, this thing which depends on the past value, which is kind of like a momentum thing. And then it's called the sequence memory, which is fed in through the gates. And so basically it has two kinds of state variables. It has Markovian state variables, and it has what I like to call gate states, or contextual state variables. And if you think about it, where did this idea come from? It came from language to language translation, where the meaning of a sentence depends on the order of the words and what you said earlier and what you said later, right? That context information, the reason your language to language translator knows how to translate correctly from English to German or to any other language is because that context information is actually learned by this contextual state, okay? So here's that basic unit. We call it a gated recurrent network. It's the general term. And so these pathways, this is the Markovian state updating pathway, which is very common to us as physical scientists, right? All our physical models are built using this principle. And then they have these interesting things, which are information flows, okay? So this thing called the remember gate, they call it a forget gate. I like to call it a remember gate, which is more accurate. It learns from the inputs, it learns from the outputs, it learns from the cell state. All of the gates learn from all of these things, right? So you get this complicated connectivity going on inside, okay? Which makes it more flexible. And you put in all these time delay information so you can remember what happened in the past. Was I talking about cars, or was I talking about cats, or was I talking about pigs? Yeah. All right. So that's the theory part, okay? Now we're going to use it. So how can we use this to do science? So hopefully you're all familiar when you start learning modeling in hydrology or the domain sciences, you always start with this simplest possible model, which is like a bathtub, right? You have your tap, open the tap, water pours in, and water comes out the hole at the bottom if you don't plug it up. And whether the water increases or decreases depends on the rate at which water comes in and how fast water can go out, right? So it'll fill up until it reaches a steady state, or it can vary, okay? So this is like the water going into your bathtub. This is like the water that's accumulated in your bathtub, and this is the water coming out. And that depends on how much friction there is in this hole at the bottom of the bathtub. Yeah. So your conservation equation applies, right? The rate of change of state is the input minus the output. And you've got some kind of a flux equation which says the output depends on the state through some relationship, okay? So this is how we typically model. But what if I do something interesting? I take this equation over here, and X is the state variable, and I divide and multiply by the state, okay? And I rewrite this to look like this, where this term K is a conductivity term. It says how much of the state comes out as the output at each time step, okay? And now what does that look like? That looks exactly like our LSTM gating equation, okay? And so this is a time-varying conductivity term. And the idea is I want to learn what this is. And I can rewrite this continuous time equation in discrete time, and I just fill in the terms and rearrange them. And basically, I'm back to my exact same equation that I showed you in the theory part, which is the equation of the LSTM, or a basic standard linear modeling dynamical system model, okay? I've added one more constraint, which is not in the LSTM, is that I need to conserve mass if this is mass, or energy if it's energy. And so I put this one additional constraint in, okay? So here's my modified LSTM node, okay, which is now modified to conserve mass or energy. But now I need to add another term, right? Because if I'm modeling water processes, some of that water is going to be lost through evaporation, right? Trees put their roots down into the ground and they take that water in. So not all the water that goes in is going to come out as stream flow, right? Or if I leave the water in my bathtub long enough, it's going to evaporate, right? So we added this additional gate, which is not there in the LSTM, which is called a loss gate. And we're going to learn all these gates. So we got an input gate, that circle should be down here. We got a remember gate, we got an output gate, and we got this loss gate, okay? And our equations are basically going to be very similar with this additional constraint that the sum of these three gates has to be equal to 1 in order to conserve mass, okay? All right. Very simple concept. We've just taken the LSTM architecture, adapted it to do physically based modeling, and now we're just going to test it on a simple case. Okay. So we're going to apply it at the beginning to this simple problem of modeling this catchment dynamics of the Leaf River, Mississippi. It's a very humid catchment. I've been using this data set for 40 years, apologize, but it's the first place, go-to place you test an idea, okay? So you've got precipitation as mass input, you've got potential evaporation, which tells you what the energy levels are, and you've got stream flow, which is your mass output, and you've got this unobserved loss of evapotranspiration that we talked about, evaporation, okay? So this is our node, and instead of building a very complex LSTM system with 256 nodes or something, I'm just going to see what's the performance of a single node, okay? I'm going to drive my ET loss with potential evaporation. That's my energy, which is an information flow. Remember, this is mass flow. I'm going to drive my output gate, just depends on the cell state, and I'm going to enforce mass conservation. Okay, so here's some results. I'm going to show you this is a single cell state model. I'm going to show you out of 40 years, I'm going to show you the smallest peak here, right, which had the smallest peak in it, the driest year. I'm going to show you the medium peak here, some sort of average, and I'm going to show you the largest peak here, sort of the one which had the biggest flood in it, okay? And this first model, I'm going to keep the gates constant, like we do in a linear reservoir type of approach, So no variable, I'm not going to learn the gates. I'm just going to learn weights like in an artificial neural network that are constant. And that's like a linear reservoir with a constant rate of evapotranspiration. And you can see, I hope you can see, you got pretty flashy response. You're not doing very well at all, whether you're on the dry year or the medium year, and you're not doing too well on the wet year. You're missing these peaks that you want to predict. I can take the loss gate, which was constant, and make it variable. So you learn an evapotranspiration response to energy, and it doesn't really improve anything very much. I can then set the evapotranspiration gate to a constant, but learn the output gate, a variable output gate, okay? And now you can see I'm starting to do really a lot better. I'm hitting this peak right up there. And now I allow both gates to be variable, and you can see a pretty good response, although there's still some stuff going on over here, and we're not quite sure, but it may have something to do with poor precipitation in dry years, poor precipitation measurement in dry years. Okay, so you've got this, we've effectively built a nonlinear reservoir with variable evapotranspiration rate. And there's a picture of it so you can see it clearly. And you can see we're actually doing really well. We're tracking the peaks. And so you know, we could use an LSTM and we'd be able to predict accurately this thing and do flood forecasting, but we wouldn't be able to understand what it was doing. And here, just using the simple node model with a model that I can actually understand, I can actually predict a very good behavior, probably comparable, okay? We will run some tests to compare. Okay, but that's just 1 year, right? So what about all the other years? Maybe I just picked the 1 year to show you which was the good one, right? So what Yuan did was he took the 20 years, the 40 years, and he computed the performance metric for each of those 40 years. And so what we're showing you is the distribution of that metric. Again, we want 1 up here is perfect. He's computing the distribution of the metric over 40 years. And you can see the median performances here, what we were showing earlier. But now you can see that there's some variation in performance, and some of the years are really doing badly, okay? So which model is this? This is the one which all the weights were constant. This is the second model where I allowed the ET to have a variable rate. This is the third model where I allowed the output to have a variable gate. And this is the fourth model where I allowed both the loss and the output to have variable gates. And you can see performance is going up. The distribution is narrowing down. This is what you would like. So learning context-dependent gates really helps. But what's even more fascinating to me is look at what happens to the worst year, right? We always tend to focus on the best year. We tend to focus on the median year. What I really want is my worst year to get better. Otherwise, I don't know if I'm really learning. And you can see that the worst year goes from really bad, below 0% efficiency, all the way up to about 50% efficiency. So gating really, really helps, okay? Then we did something, we said, well, but maybe it's evaporating more water than it's allowed to. I've got a potential evapotranspiration constraint, so I'll put in a PET constraint. Same model, I just constrain it so it can't evaporate more than the potential rate. So I put in a physical constraint, and the performance is more or less the same, but it gets a little bit worse, okay? So this illustrates the fact that when we put in physical properties to a machine learning model, it can actually make things worse, right? If we don't know what we're doing, okay? All right. What do those gates look like? So here's the output gate. Here's the cell state going from 0 to 1 meter of water, right? This is the soil moisture zone. And you can see at about 60 centimeters, it's suddenly doing a very strong threshold response. So below about half a meter, it doesn't want to generate any streamflow runoff. And above about 70 centimeters, then it's sort of generating at a constant rate above that, okay? So it's got the steep threshold-like activation. How does that cell state vary with time? It does this. So this is where that flood peak was, and this is where the other flood peak was. Here's what the loss gate looks like for evapotranspiration. You can think of this as the flux equation, right? How do I compute evapotranspiration? And this is what that looks like as a fraction. And you put them together, you get the remember gate. It looks like that. And it basically says in this wet catchment, most of the time it's retaining about 95% of the water. It's only losing on average about 5% of the water to evapotranspiration and stream flow. I'll skip over this quickly, but basically just to show you, we separate the data into training, testing, and selection to make sure we're not force fitting. And you can see that it doesn't matter which data set we use, performance is uniformly good. The variance ratio goes to 1 as it should, the bias ratio goes to 1 as it should, and so on. Okay, we'll skip over that. And then we said, okay, but that's only a single node. And this is hot off the press. Yuan just sent me this morning, so I added it in. So what happens if I actually construct a physical model, right? Here's my surface soil moisture zone. There's my routing, river routing tank, and there's my groundwater tank. So I feed that in. Oh, I forgot to mention, this entire thing is programmed in PyTorch, everything is trained using machine learning technology, right? None of the global optimization stuff. Everything is trained just like a machine learning algorithm, okay? The only thing that's different is that we're putting our understanding of physics into the model, okay? In the way we design the architecture. Okay, so this is about the simplest possible physical conceptual model that you would typically imagine, okay? Already with one single state, we're predicting a daily timescale, and we're doing really well, okay? Why would we want to go to a more complex model, okay? And here's why. So again, you've got the smallest, the median, and the largest peak flow year, okay? You can see these look pretty much the same, but on the bottom, I'm plotting the same data, but in a log scale. So that's emphasizing the low flows, right? The small values, which are the recessions, which you can't see in the top plots. And here's the single node model, okay? That's the black line. So what you couldn't see on the other plot was that it was really not doing a good job when you were predicting low flows, which would be important to you if you wanted to manage fish populations or things like that, right? What happens when we put in that more complex model is we get this blue line, okay? So it's not perfect, but it's apparently adding that extra capacity or architecture has enabled it to improve its performance because of this groundwater tank and learning what's actually happening in the periods which are dominated by low flow recessions. Okay. All right. So that's what we've been able to do so far. Basically, to summarize this, the traditional machine learning approach is basically to treat all your data as information flows. Okay. But in principle, you could add physics to it, right? But at this point, everything is treated as information flows, whether it's mass, energy, or other kinds of information variables. The idea we're developing is, what if we are able to use this machine learning approach, but separate out the ability to separately model mass flows, energy flows, and information flows, 3 separate parallel pathways, and then they share information amongst them. Where do they share information? Through those gating mechanisms that I talked about, right? So you get the central pathway, which just models mass. Let's say you're trying to model snowmelt. You need to model mass accumulation and propagation through the system. You need to model energy accumulation and propagation through the system. And you need to be able to take advantage of other pieces of information that are neither mass nor energy, right? So we'd have these 3 pathways and they would share information. And the idea is that hopefully we would be able to build a more comprehensive approach to using machine learning technology, but to build physically interpretable systems along the lines of what I was showing you with these very simple examples. So I'm firmly convinced that machine learning is going to be a big and important part of the future of the domain sciences, regardless whether it's hydrology or not. I'm not the first person to say this, but I'm saying it. And it's important, therefore, that there's a very strong conversation between people on both sides, right? There's a tendency for hydrological scientists to go, yeah, we've been doing machine learning forever, so what's new? Well, there's a lot new, okay? And there's a tendency for machine learning people to say, I don't need to understand any domain science. I can give you better forecasts than you can do with your physical models, right? Well, maybe, right? I still need to understand what's happening. In my view, it makes possible a much more powerful approach to science, and it gives you sort of a structured approach to discovery. And I'll stop there. Thank you.